So as we begin Lecture 2 for Module 1 for ME14, we want to go back and do a little bit of an overview of what we're recovering within this chapter and within this module. So this Module 1 is going to be the introduction and the concept of stress. Now for objectives within this chapter, we're taking a look at and reviewing statics that's needed to determine forces and members of simple structures, going into the concept and introducing the concept of stresses. We're going to define different stress types. These include axial normal stress, our shearing stress, and our bearing stress. Another thing that we're going to talk about here is the discussion of the engineer's two principal tasks, analysis and design of structures in different machines. We're also going to talk about developing a problem-solving approach, and this is something that's going to be very important as we move on with some of our other courses. We're going to discuss the components of stress on different planes and under different loading conditions. And last, we're going to talk about the design considerations that an engineer should review before preparing a design. So how does this relate to our textbook here? Well, this is Chapter 1, the concept of stress. The first two sections are going to be a review of the method of statics. So that's section 1.1 and 1.2 in your book. 1.3 and 1.4 are going to cover stress, member of a structure, oblique plane, and under general loading conditions. And the last section, section 1.5, is where we start jumping into some of these design considerations. So now that we've done a little overview of what we're going to see within the entire Module 1, we'll jump into our second lecture, Module 1.2. And this is where we're going to start looking at the concept of stress here and going through our learning objectives that we discussed in the previous slides. Within this module, we're going to take a look at some applications, some key equations, and problem solving. And if you relate back to Chapter 1 in your text, there's some great problems as well that I would recommend that you go through in the textbook. So the book that we're going to be utilizing here, again, this was in your syllabus, and we went over this in the first lecture, but again, this is going to be Mechanics of Materials, the 8th edition here that we're using here by Beer, and this is available in the bookstore, but if you are sharing a textbook with another classmate or you have an older 7th edition or an E version of this book, that is fine as well. I still will be posting all of the homeworks written out for the problems on Blackboard, so you won't necessarily need to have your own copy, but I would encourage you to have something to do the readings with, whether it's an older version or a shared textbook. The readings and the material within this textbook are crucial for this course. So, overview of the course itself. We've seen this in our syllabus, but these are the general areas that we'll be covering throughout this entire semester through all 15 modules. So now this brings us to the beginning of Chapter 1, Section 1.1. We'll start talking about this concept of stress. So our main objective of the study of mechanics of materials is to provide a future engineer, as you go out further in your career, wherever that may be, with a means of analyzing and designing various machines and load-bearing structures. So we're taking the information that we've learned within our statics and our dynamics courses and expanding upon it from there and talking about a little bit of designing. What other factors are going to come in? We've made a lot of big assumptions and generalizations in our statics and our dynamics courses. Now we're going to need to take some of those things into account and bring them into some of the problems here. So as we continue on with this concept of stress, both the analysis and the design of a given structure involve determination of stresses and deformations. And those are things that are going to be very important that we need to consider. This chapter is going to be devoted to this concept of stress. So the next thing I want to do is go a little bit of a review of statics. So what we can see over here, we have a boom that's going to be used to support a 30 kilonewton load. So we have over here, okay, these are fixed to the wall. Right there, we got these two pin joints, one at C, one down here at A. We know the distance between these two guys here, between A and C, is given to us as 600 millimeters. We can see now coming off this pin joint here, we have a member here that's 800 millimeters long coming out here to our external load of 30 kilonewtons there. Another pin right there at B. This length from C to B. We don't have it here given specifically in the diagram, but we can say, you know, this squared, 600 squared plus 800 squared is equal to the square root of the hypotenuse over here. So we can go ahead and calculate that out using Pythagorean's theorem. They do tell us here the diameter of this member here is 20 millimeters. So this is something that I like to do. That thought process I had right there was kind of to show you guys what I do for any of these problems that we have in our book, whether it's a review problem, an exam problem, a homework problem, or just an example problem we're working through. I really like to first take a look at what's given to me in, one, the problem statement, and two, the initial given diagram. So over here, I'm really looking at that. I'm seeing all the different geometries, dimensions they gave us. What can I kind of deduct from how things are set up here, all that information. So that's just looking at the diagram. Then I can come over here to the wording of the problem here. They tell us we have a structure. It's designed to support this 30 kilonewton load. Well, I've already looked at my diagram here. Now, okay, there's my 30 kilonewton load that they're talking about right there. The structure consists of a boom, AB, and a rod, BC. So let's go back over to our diagram and take a look at this. So boom, AB. Well, here's A. Here's B, so this is our boom AB. And again, I can see that this is 800 millimeters long and 50 millimeters thick right there. And then we have rod BC. So there is B, there is C. Here's our rod BC going along this length right here. And again, we can tell this has a diameter given to us as 20 millimeters. They tell us here that these are joined by pins, and we can clearly see those pins right there, A, B, and C. 0 moment connections right there from the pins at the junctions and supports. So now we've got the wording and we've got the diagram. We're starting to compare these two together. What do they ask us to solve for? Well, they want us to perform a static analysis to determine the reaction forces at the supports and the internal force in each structural member. So this ties into how I kind of expect you guys to set up and solve your homework problems. Take a look at the diagram. Take a look at the given information, the problem statement. Write out in a clear, concise manner. What do I know? What information do they give me? With all that written out, our chosen coordinate system, our given diagram, from that, we can say, okay, now what are they asking us to solve? So I'll put a find section there, and what are they asking us to solve for here? In this case here, reactionary forces at the supports. So that's how I would set up this problem here. Now, along with that, we put any assumptions that we have down there. From this one here, we're already looking at this, and I'm already thinking before I even start solving the problem, I'm probably going to want a free body diagram here. Going to be looking at some forces here. Probably going to need to do out a little bit of trig, some geometry tricks in here, all that information. So this, again, for this problem here, I really wanted you, as a review of statics, think about how you set up the problems. What information is given to you both in the problem statement and the initial diagram? What are they asking you to solve for? What assumptions you are making? What your plan of attack is to solve this problem. So now that we've read through the problem, had a chance to really understand what they're giving us for information, what they're asking us to solve for, and kind of formulating a basic plan of attack in our heads, now we can actually start the solution to our problem here. So this right here is the solution section, and what we're going to be looking at first is our free body diagram. So what we can do here is we can see off on the left, we have these two members, our C to B and our A to B members right there, and we can do out our free body diagrams. Now we can do it as we see here, as all kind of one, or sometimes even this gets a little bit complicated and it's better to do these out individually. Do a free body diagram for member AB, do a separate free body diagram for member CB as well. So when we're doing a free body diagram, what we want to remember is we're talking about reactionary forces in this problem here, and that's what they're asking us to solve for. So we can see, okay, these guys right here at point C and point A are going to have reactionary forces at them there from where they're connected to the wall. So there's going to be two directions that you can go in. You have your CX and your CY for your reactionary forces at point C, and you have your AX and your AY for your reactionary forces at point A. I draw out. You see now what we've done here is we've converted to meters. So everything was given in millimeters. This is something that's very important as you're setting up these problems here, is to keep track of your units and make sure you're consistent. So before we were in millimeters, we know that most of our equations we're going to utilize are probably going to be in meters. So we want to make that conversion, and I like to do that right at the beginning of the problem here. Okay, there's my 6 meters, or sorry, 0.6 meters, and down here this is now 0.8 meters instead of being in millimeters. The next thing for a free body diagram, we say, okay, what other forces are acting on it other than our reactionary forces there? Well, we have this external load acting at B right here, given to us in the problem statement as 30 kilonewtons. So we can draw that in there, and this completes our free body diagram. Now, as I'd mentioned, you don't necessarily need to do these all in one. You can do out 2 separate free body diagrams as well. Pros and cons to both. A little bit more work, a little bit more drawing, draw out 2 free body diagrams, but it's a little less congested, easier to follow, especially as we get complicated. There's 5, 6, 7, 8, 9, 10 different members within a truss problem like this. you might want to break things down into individual free body diagrams for that. So now what we can do is take a look at our summation of moments and our summation of forces. And we recall that from our statics courses as well. So we can say, okay, we can do moments about a couple different areas. Let's just take here and say, let's do our moments about C right here. So we can go through, figure out what are our moments about C. And we recall for moments, it's going to be our forces times perpendicular distance. So by putting it at C, our CX and our CY are not going to create a moment about C. What is going to create a moment about C is our AX component, because our AY is directly in line with it, so that's not going to create a moment. There's no perpendicular distance, force or perpendicular distance there, that's in line with it. Whereas our A of X over here, it does have this perpendicular distance here of 0.6. So that's where we have our AX plus our 0.6 meters right there. Then we also have now down here our external load times this perpendicular distance right here of 0.8. Now, the other thing to notice when we're doing moments again as a refresher is to pay attention to your sign convention. Use your right-hand rule. What's going to be a positive moment? What's going to be a negative moment? So if we look at A coming in here, going around counterclockwise, we do our right-hand rule. Okay, that's going to be a positive. So you can see that's a positive moment about C right there. And I've clearly labeled this. Going counterclockwise, I'm considering to be positive for this case here. I'm considering my X positive to the right, my Y positive going up with the standard Cartesian coordinate system. So that's something I also would encourage you to do. With a problem like this, clearly put this up here for you, for the grader, for whoever. So you remember, okay, I'm considering X positive to the right, and I'm considering Y positive going up there. So do that out, and that's why now when I do my 30 kilonewtons here times my 8, and I do my right-hand rule, my thumb's going into the board, then I can see, okay, now I have a negative moment here, and you can see there's my negative sign right there from that negative moment right there. I can take a look at this, and I can say, okay, well, my only unknown here is my A sub X, so from this right here, I can directly solve from summation of moments about C for my value for my A sub X. So the next thing I'm going to move on to is summation of forces in the X direction. So I take a look and say, what forces are acting in the X direction? Well, I have this A sub X force here, and I have some C sub X force right there. So I can say, okay, summation of force in the X direction is 0 from Newton's second law, F equals ma. It's going to be equal to 0 on the right-hand side if nothing's moving for statics. Their acceleration is 0. So we have our forces right here. Now our A sub X plus Cx is going to be equal to 0 because these are both going positive direction. This is my positive X direction here. Positive X direction there. So AX plus CX is equal to 0. Well, we have a value for AX right there that we can plug in right there. So therefore, when we write this out here, rearrange this. If AX plus CX is equal to 0, then CX is equal to a negative AX. We can plug in our A value from up top here into our AX there. So therefore, our CX is now negative 40 kilonewtons. So now we have a value for CX and for AX from doing our summation of moments about C and our summation of forces in the X direction. So lastly, what we can do now is take a look at summation of forces in the Y direction. And this is where we need to stop and think. It's easy to just keep plugging and plugging and plugging in these problems like this, but this is why it's very important to have that first page where I talk about having your given information and your find information and understanding what you're looking for. So as we get to this point, like, okay, what am I really solving for? Go back to my beginning page here, my setup page. Oh, I'm solving for my reactionary forces. So I'm going to need my CX, CY, AX, and AY. That's what they asked me to solve for in this problem. So that's what I'm going to go back and make sure I have. So far I found my AX and my CX, but I don't have any of the Y components. So that's why we're going to jump into now our summation of forces in our Y direction here. We go back to our free body diagram. We say, okay, I got a CX and I got a CY and an AY, both acting in the Y direction here. Summation of forces in the Y direction. So we have 0 is equal to AY plus CY minus 30 kilonewtons. Well, this is our third force down here. This we already have a value for, and this is acting in our negative Y direction, hence our negative sign right there. So from this right here, we have that when we rearrange this, AY plus CY is equal to, move this over to the other side here, 30 kilonewtons. Well, get a look at this and we say one equation, two unknowns. So we need a secondary equation, a relationship between AY and CY in order to solve for both of these here, because we have, again, two unknowns in one equation. Our number of unknowns need to match our number of equations or relationships. So now that we've determined we have more unknowns than equations, we need to figure out another equation, another relationship in order to relate these reactionary forces. So now we did that structure free body diagram in the previous slide. So now what we can do, what I kind of briefly mentioned here, and look at the individual components and the free body diagram associated with that. So we already did our moments about C. So what now if we did our moments about B? So we can take a look here and we draw out our free body diagram of just this member AB, freed from the entire structure, and just looking at it as an individual member here. We need to make sure, in order if we're going to do this and separate it from the structure, that we have all the correct attached reactionary forces. So the difference is here, well, we already saw at point A, we know it has reactionary forces AX and AY where it connects to the wall at that pin joint there. But what we need to do when we break this apart from our other structure, from structure BC, from that rod, is realize that there's going to be a reactionary force where that rod connects to point B down here on member AB. And this is going to have its associated reactionary forces of BX and BY there. So that's why when we draw this out, we didn't see these reactionary forces for the structure as a whole. We only saw this external load down here of 30 kilonewtons. Well, this is important when we break these apart. This is how we connect those two. So if we wanted to look at these from the beginning as individual free body diagrams for each of these members, then you would also see the same BX and BY reactionary forces on that rod going from B to C. And that's how we relate those back to the structure themselves. So as we're considering this free body diagram for this boom AB, we again draw, okay, if we're going to take our summation of moments about this point B right here, I'm going to again say positive going counterclockwise for my moments. And by doing it about point B, what we do is we eliminate a lot of things. And that's a good thing to do. So we're looking at these problems and we're solving through them. How can I make this as easy and simple as I can to solve it? Well, I'm looking at all this, and if I put it at A, I've got all three of these over here. But if I do my summation of moments about B, then BY, BX, and our external load do not create a moment about B because they're all right at B. Force times perpendicular distance, there is no distance. They're all right at B. So I come over here and I look, well, AX isn't going to create a moment because there's no perpendicular distance there. So the only force that's going to have a perpendicular distance that's going to create a moment about B is my AY. And that's one of the two unknowns from the previous slide that we need to solve for. So that works out fantastic. This is something you want to think about before just jumping in and trying to come up with a random third equation or an equation to match the number of equations and unknowns is, what am I looking for? What do I have? So that's important there. We do that out and we say, okay, the summation of moments about B is equal to 0 in statics here. Well, the only moments acting about B are this force times the perpendicular distance. So having that there, we can plug in. We don't know, this is what we're solving for, our AY, and we know our perpendicular distance here is going to be this distance away from point B here, which is 0.8 meters. Now I do this here, take a look at my right-hand rule. Okay, if it's going this way, my thumb's going back into the board there. That's going around clockwise, not counterclockwise, so therefore this is going to be a negative moment. There's my negative sign right there. So from this here, I can say that my only unknown in this case here is my AY. So AY times point A is equal to 0. Well, then AY is equal to 0. Now I can take that information, go back to my equilibrium equation on the previous slide there, plug in this value for AY because it was one equation, two unknowns. Well, now I know one of those unknowns is 0. I plug in 0 for AY, and when I do that, I end up getting a value for my CY, which then gives me all my reactionary forces, which is what they asked me to solve in the problem. So down here, my final solution right here, I write my results section out, clearly labeled. Well, my A is 40 kilonewtons here. We have a CX and my CY here. And this is something that's important to do. You can see, yes, it's positive. And I'm saying right here with this little arrow notation here, it's positive because it's going to the right. We can say here, this is 40, but it's negative because it's going to the left. And then this is my CX right here, which is positive going up. The other way you could do this is, again, write out your chosen coordinate system here. My Y is positive going up. My X is positive going to the right. And then you can put negative and positive signs there. So there's multiple ways to do this, but you really do want to pick the best one that helps you keep track of sign convention. It doesn't hurt to do both. That way, if you're going through and you accidentally drop a negative, your grader can take a look and be like, oh, okay, they just lost the negative, but they know it's moving to the left. They know it's going to the right. They know it's up. It's going counterclockwise, wherever it may be. So as we continue on with the same problem here, what I want to take a look at is the method of joints. So joints must satisfy the conditions for static equilibrium, which may be expressed in the form of a force triangle. So if we look over here at our diagram on the left for A and B, we can see on the left in part A, we have our point B here from our problem before. We have our external load of 30 kilonewtons acting right there. Now what we can see is we have the force, remember, AB coming in here like this, and we have a force from BC right here like this, going up to a point C over here and a point A over there. Now what we can do is we can move this external load here up to this point over here to create this triangle that we see, our force triangle over here on the right in part B. So now if we take a look at our dimensions here from our original problem, we can see that this is a 3, 4, 5 triangle. 3 squared plus 4 squared is 5 squared. So we can use this information in order to solve for these forces based upon our known force right here. So we have geometry and forces, and this can go all the way back to pre-calculus, the stuff that we saw in high school to get these arrangements as well. What we're going to do is we're going to use this force triangle here. And what we'll say, we can see here the summation of forces on point B is equal to 0. Equilibrium here, static equilibrium. And now what we can do is we can plug into this triangle here. So we can see that our 30 kilonewtons over this length right here, this is our 3 side right there, over 3 like that, is equal to now our F sub B over 4 right there. Sorry, F sub AB over 4 right there. So there's our F sub AB over 4 right there. And this side right here, our F sub BC over 5 right there, F sub BC over 5. Now with this here, we can simply cross multiply to find our unknowns here. So we can say that FBC times our 3 right here is equal to 5 times 30 kilonewtons. 5 times 30 would give us 150. Take and divide by the 3 on this side here is 150 divided by 3, which equals now FBC is equal to 50 kilonewtons. So that's how we get that, by just cross multiplying through there. We can do the same thing now with our FAB, and what we find out when we do that there, our FAB is equal to 40 kilonewtons. So one thing that we want to note here is that the boom on the bottom side over here and our rod, or our boom right here and our rod right here, are 2 force members. Therefore, the members are subjected to only 2 forces, which are applied at the end of the members. Now, for equilibrium, the forces must be parallel to an axis between the force application points, equal in magnitude and opposite in direction. So as we continue on and begin this mechanics course for ME14, we want to take the information and knowledge and skill set that we got from our statics course and expand upon it for some more in-depth questions and problem solving. So this is where we get into now our stress analysis portion here. So let's just say the same problem, and now they ask us the question of, can the structure safely support the 30 kilonewton load if the rod BC has a diameter of 20 millimeters? So this is something we saw in the initial problem. When our diagram, this was given to us at 20 millimeters, and we hadn't used it to solve for our reactionary forces. We hadn't used it to solve for the forces in our members. But now, this is where we'll bring it in for stress analysis when we answer the question of, can the structure safely support this load that's applied here in our diagram there if it's only 20 millimeters in diameter? So from the previous slide here with our calculations from the static analysis, we were able to calculate our compressive force F sub AB and our tension force FBC here of 40 kilonewtons and 50 kilonewtons respectively. So now what this tells us is that at any section throughout the entire member BC, so here's our CB, so this is member BC right along the top right up here, the internal force is going to be that 50 kilonewton tension force that we calculated on the previous slide, with a force intensity or stress, this is where stress comes in, given to us by the following relationship. So we recall our relationship between stress, force, and area. So our stress, our sigma BC for this member BC right there, is equal to our load over our area, where our load right here is 50 times 10 to the third newtons. Now I want to stop right here for a second and talk about units. So all along the way, we've had things in kilonewtons that we solved for, but now that we want to deal with this here, we want to make sure that our final units are in MPa, so we don't want to be in kilonewtons anymore, we want to be in newtons, so this is no longer 50 kilonewtons, but it's 50 times 10 to the third newtons. So always take the time to stop and double check your units, and I would highly encourage you to do unit analysis. Place your units in the problems, in your equations as you're going through, solve, cancel things out, and make sure they end up in the right units that you would expect at the end, and you're not off by a factor of 10 to the third because you were in kilonewtons instead of newtons. So with that in mind, we go down to our denominator here, which is A, and A is our cross-sectional area of our rod here. Now, a couple things we need to take into account here is, one, they gave it to us in millimeters, make sure we convert to meters. And two, they gave it to us a diameter and not a radius. So our area, our cross-section area, is pi r squared. So we take this d, divide it by 2 to get our radius, which is 10 millimeters. Make sure we convert it to meters. When we do our pi r squared, then with it as the radius in meters, we end up with 3.14 times 10, sorry, 314 times 10 to the negative 6 meters squared. Now we do this out here, newtons per meter squared, so we end up with our megapascals over here when we cancel out our exponents right there, and we end up with 159 megapascals when we do the unit conversion, and we have everything correct with our equation. So that is our stress in BC. So now what we need to do is we go back to our tables for the properties of the individual materials. So if this is a steel, we can take a look at our lookup tables here and say, okay, for steel, the maximum allowable stress is sigma of 165 megapascals. We're only at 159 megapascals. So therefore, the conclusion is that the strength of member BC is adequate. So now we've gone through, looked at our stress, and determined that yes, if we make this out of steel, that given 20 millimeter diameter of our rod from B to C is adequate. Well, now comes down to design. So we can't always make everything out of what we'd like to make it from an engineering standpoint. A lot of times weight, cost, expense, machinability, all other types of external factors may come in. Maybe it's a case where there is a corrosive environment and you can't use steel. So therefore we either have to look at stainless steel, and maybe the cost is too high with stainless steel. So then we're looking at titanium. Cost is still too high. Maybe we need to go to an aluminum. So whatever the case may be, you know, for reasons based on, like I said before, on cost, weight, availability, design criteria. Maybe you're working on a grant. They don't tell you why, but they say you have to use aluminum. Things like that come into play when you're talking about actual practical design applications. It's no longer just a problem in a book, and yes, we can do it exactly how we want it to make it as strong as possible. Well, now we got to take all these other factors into account over here, so we need to redesign. So the question was, you know, is it going to be safe and sturdy if it's out of steel and 20 millimeters diameter? Yes, it is. But now, okay, let's reverse that question and say, what would the diameter, what would the dimensions of this need to be if we were to use aluminum instead of steel? So we can go back through, we can still do our stress calculations here. So our stress right here, we can see for this guy here, for our load over our area, we already know that our load, we've calculated that there. And we have a sigma over here, so we reverse the equation. So rather than before where we knew our load and knew our area, now we know what the allowable stress should be, and the question is, what is the area based upon that? So we put in our load, and now we can reverse that there, and we say that P over A is equal, P over our sigma will give us an area here. So we have this area right there. Now if we have the area, we can reverse that there, back out a diameter from our area there. So if we were using aluminum and we knew what our sigma here for aluminum was, we can back out and get what the diameter of that rod would need to be in order to safely support that 30 kilonewton load right there. And we do that calculation and back it out. What we find is that the aluminum rod, if we choose to go with aluminum, needs to be at least 26 millimeters in diameter.